there's one last example I want to talk about that's related to the dot product. So here we go. In physics, we have that work is the product of force and distance. So in other words, we have an amount of force, and we move something a certain distance, multiplied together, and that's the amount of work. Now, when we move up to higher dimensions, even higher here meaning 2, we have the idea is that really we have force is a vector, because you apply force with a direction and a magnitude. So now we're going to have a vector F. Now, on a side note here for notation, notice that here the F is just bolded. So you'll see this from time to time, where there's two conventions. You can either have F as a bold or F with an arrow on top. Both are fine. Okay, so this is a vector, that's our force. And now we have a vector, which is the displacement. In other words, we're using a force and we're moving something, and how much was it displaced? And so the question is, well, what's our new equation for work? So to get some idea about what's going on, imagine for a moment you had a big snowstorm and you have a car, and you can see by this excellent drawing that this is a car. All right, well, it's stuck and you want it to get freed. What do? Well, you hope that you're in Iowa, surrounded by nice people, and you say, aha, all of a sudden a lot of people come to your aid and they start pushing. In fact, there's so many that come to your aid, they can't all fit behind the car. And so some people are pushing from the back. We could call these people effective. And the other people pushing from the side, we call them not as effective. Because what's happening? Well, some of their effort is being used to push the car in the right direction, and some of their effort is being wasted. In essence, what's happening is some of their effort, that's the useful part, and then some of their effort is really trying to push the car sideways. Not very useful. And so what we want to do is figure out, okay, how much of their effort actually goes into moving the car forward? Well, that's like a projection. And so it's a natural thing to think this might be a cross product type question. Okay, so let's think about our setup here. I have my vector. Here's my force vector F, and there's this displacement vector D. So this is how much it's going to move. So what do I have? Well, what I can do is I can say how much of F is pointing in this direction, the direction that I actually move something. So if we want to figure that out, let's sort of draw ourselves a picture here. We drop straight down from a right angle. There's a little angle theta here. And I say, this amount, that's how much of the force is actually being effective. Well, how much is that amount? Well, think of a right triangle. Got the hypotenuse, and I have the adjacent side. That's what I want to know. So cosine theta relates them. And in particular, I can say that the magnitude of F times cosine theta, that's how much force is actually being used in the right direction. Well, okay, so that's really the substitute for that capital F from our original formula. Well, what's our distance going to become? Well, our distance is how much the displacement changed. So that's going to be the size of D. So the magnitude of D is D. So this is our work. Size of F, cosine theta times size of D, where theta is the angle between D and F. Aha! Well, that's the dot product. Magnitude of the vectors, cosine angle between them. So this is F dot D. And there you go. Now you might notice, hey, it's really similar to what we had before. Coincidence? No. In fact, there's this beautiful sort of things generalized in a nice setting. So that's good. That's good. All right, well, that's the end of the dot product. So now we're going to keep moving on. And we're going to talk about vector products. So we're going to have a total of 3 vector products in our class. And we've talked about 2 of them already. Now, you're probably thinking, wait, we've only done 1. Okay, we've actually done 2. So what are they? Let me grab the sheet here. The first one is the scalar product. So what's the scalar product? Well, the scalar product is when you want to scale something. So the way you do a scalar product is it's a number and a vector. And the result is a vector. It's the scaled vector. It's good for changing length. So for example, we use it when we have unit vectors. Now, be careful with notation. So if you ever see number vector, notice there's no like dot, there's no crazy symbol. It's just number vector. Okay, dot product. Dot product, well, what's that? That's a typo. A very bad typo. We're going to fix that typo. That's a vector, dot a vector, and you get out a number. So vector, dot vector, the result is a number. Okay, well, what is that number? Turns out, as we saw last time, it's the magnitude of u, magnitude of v, cosine, angle between u and v. And this part right here says the dot product, it means something geometrically speaking, because none of these things are coordinate sensitive. What can you do? Well, we can find angles using the dot product. And the reason we can do that is because we can find cosine theta. What else can we do? We can test orthogonality, because two things are orthogonal if and only if their dot product is 0. And we can do projection. And projection says, I have two vectors, u and v. And I say, how much of u is parallel to v? In other words, I can think of breaking u up into two things. One thing that is some multiple of v, and another thing which is perpendicular to v. And this says, what is parallel to v? So it's the u dot v over v dot v times v. Okay, so what do we have? Well, we can scale, and we can take two vectors and get a number, but it's not quite very satisfying. What we'd really like is a product where we take a vector and take another vector and get a vector. And that is possible. Well, almost possible. There's a caveat. This is called the cross product. What's the caveat? It only works in dimension 3. Now, what's special about 3? Well, 3 has a very nice property. It turns out that mathematicians have shown 3 is equal to 2 plus 1. And the only number which is equal to 2 plus 1 is 3. And so that's it. That's why. Now you might think, that's a joke. It's actually true. It's actually true. So let's talk about it. So if I'm looking for a cross product, which says I want a vector cross a vector to get a vector, I say, well, okay, let's talk about that vector. What properties does it have? And in particular, we say, well, if I ever have a vector, I need to understand two things about that vector: the direction of the vector and the magnitude. So let's start by talking about the direction. So the direction of the cross product. And here's the rule. So u cross v is going to be perpendicular to both the original vector u and the original vector v, and it obeys the right-hand rule. So let's talk about this. We're going to draw a picture here. So I have a plane. So here's a plane, and there's a third direction. Now, what's the intuition here? The intuition is the following. Suppose I have two vectors, and I'll put their tails together. So here's u, and here's v. And they're both inside of this plane. So again, u and v both lie in the plane. In fact, it's always the case that u and v lie in a single plane. So that's a plane, that's two-dimensional. There's a third dimension which is perpendicular to a plane. And that's why we get the 2 plus 1. Two directions from the original two vectors plus one more direction gives us 3. And essentially what it's saying is, look, there's only one direction which is perpendicular to u and v. Well, almost only one. What's the problem? Well, the problem is, which way do you go? Do you go up or do you go down? And a priori, anything could work. So you have to have a way to break. All right, what do we mean by break? Well, there's two cases. So we need something which differentiates. Well, it's very convenient that if you look at your hands, you have two hands and they're different. So they're not perfectly the same. So they're, in other words, if you lay them on top of each other, you don't get the same thing. Okay, so hands break symmetry. So that's why there's something called the right hand rule. So how does the right hand rule work? Well, it says the following. You see, our fingers have this nice flexy part. So if this is my hand here, I can bend this part right here, and it bends really nicely. So I can even curl it all the way in. On the other hand, it doesn't bend very well in the other direction. So I can bend really well this way, and what I can think of is the following. This point right here, that's where the two vectors come together. Along the fingers is the first vector. That's U. Back along the palm is V. So U and V. So I'd come here and visualize, so I'd have U and V. And notice, one other part of the hand we haven't talked about is the thumb. The thumb will tell us which way to point. So if I have U and V, it's saying point up. So again, I'll draw a really bad picture here. Now let's see if I should go with a little bit darker green. Okay, so really bad picture coming in. All right, so again, here's the fingers. Over here, we have the rest of the hand and going back that way, and then you have the thumb. And so when you close your fingers in to make a fist, the thumb points in this direction, and in particular, it says that is the right direction of U and V. Okay, so that's the right hand rule. Now, in practical terms, we're not going to worry about the right hand rule. It just says you have to have a way to get a unique direction. The right hand rule says, among these two possibilities, which one should you take? All right, now, whoops, lots of typos on this one. The second thing we have to talk about is not direction. We already talked about direction. It's magnitude. So the magnitude of the cross product. Well, we're going to say that the magnitude of U cross V is the magnitude of U, magnitude of V, sine of theta. So it's a little different than cross product. A little bit different than dot product. Dot product, you get cosine. Cross product, you get sine. There's a good reason why we want the sine. One last thing is that we're going to say, look, I really want this to be distributive. In other words, I want to be able to multiply expressions out. So if I take U cross V cross W, I can imagine distributing through, and that's the same as U cross W plus V cross W. Or W cross U cross V, so again, parentheses here, I can multiply through, and that's, these are pluses. I am so sorry. So U plus V cross W, W cross U plus V. So it's W cross U plus W cross V. All right. So I can specify a direction, I can tell you the magnitude, and I'll tell you it satisfies the distributive property. These three things I claim are enough. And by that I mean if I have only those three properties, there's a unique way to get my cross product. Well, of course there is. Because once I know direction and magnitude, that's it. Now we want to get to the point where we can get a formula that gives us the cross product. So here we go. So let's start with some basic facts. Some of them are kind of counterintuitive. So the first one, U cross V is negative V cross U. In other words, it matters what order you multiply. So U cross V and V cross U are not the same. Well, how could we see that? The way to see that is to sort of think about what happens back here when we did our right hand rule. So when we did our U cross V, remember, you need to have it so that the angle, because if you look at it, there's two angles here. There's a angle that's less than 180, then there's a second angle which is more than 180. Well, the small angle needs to be where your hand closes up. So when you do u cross v, it's pointing up. But if I do v cross u, I need to point down. In other words, I need to reorient. So v cross u is going to cause us to go down. And so that's the reason. All right. U cross u is 0. Well, how do we know that? Well, let's go to the magnitude. So if I have u cross u, so I'm looking at u cross u, well, what's the angle between the vector and itself? And the angle is theta is 0. Well, sine of 0 is 0, so the magnitude of u cross u is equal to 0. Well, that means the vector has no change. Nothing happened. There's only one vector which is without change. That's the 0 vector. Okay. So that's how we can establish that u cross u is 0 for any vector. Now, let's talk about what happens with our three vectors that we've talked about before, I, j, and k. So if I think of this as the x, y, and z, then I have I, j, and k. And what can we do? Well, we can start putting things together. So for example, I cross j. Well, your fingers would be on the x-axis, your palm would be the y-axis, your thumb pointing straight up the z-axis. So I cross j is going to point straight up. What's the magnitude? Well, I has length 1, j has length 1, and the angle between all these vectors, actually, it's always 90. So that means I have sine of 90, which is 1. So I'm pointing straight up in the positive z direction. I have length 1, so I must be k. By the rule that says order matters, if I do j cross I, it's negative k. Okay, what about j cross k? Well, you got to remember, put your fingers on the y-axis, put the palm on the z-axis, you're going to be pointing in that direction. So j cross k is I. K cross j, negative I. And we're almost there, k cross I. So fingers on the positive z-axis, palm on the x-axis, you're going to be pointing that direction. So pointing here. So k cross I, you're going to go along the positive y-axis, length 1 again, so you get j. And if you switch the order, negative j, I cross k. So, where do we go? Well, let's do the formula of the cross product. So I'm going to start in component form, and I can only do this for three-dimensional vectors. So I have ABC cross DEF. So that's AI plus B times J plus CK plus DI plus EJ plus FK. Now, I'm going to FOIL. And by that, I mean I'm going to apply the distributive rule. And foiling really is just saying for every choice here, so there's three choices, and every choice there, again, three choices, I multiply them together and I add all possible things. So because I have three choices and three choices, there's a total of 9 things. And if you multiply them out, that's what you get. So for example, I have A cross AI cross DI. I can pull out the A and the D, and so it's A, D, I cross I. And then I have AI and EJ, so that's A, E, I cross J, and so forth and so on. Now the good news is that a lot of this simplifies. So we're going to use our properties. And by that I mean, well look, I cross I, J cross J, K cross K, 0. No need for more work. What about the other terms? Well, like I cross J, that's K. I cross K, that's negative J, and so forth and so on. So if you put all that in, what you'll get is, again, all those terms on the diagonal is 0. You get AE times K minus AF times J minus BD times K, BF times I, plus CD times J minus CE times I. And now we're just going to group things by components. So I look at what's in the I, and that's BF minus CE. What about what's in the front of the J? Well, there's a CD and a minus AF. So that's CD minus AF. And what's in front of the K? Well, that's AE and minus BD. And there you go. So you can just remember ABC cross DEF is BF minus CE, CD minus AF, AE minus BD. Boom. Done. Done. Or maybe there's a better way. Okay, so we're going to switch gears for a couple of minutes and see perhaps there's a better way. All right. So let's come back to that in a few minutes. So let's talk about determinants. So the idea of determinants are pretty simple. What we have is you have this array of numbers. And in other words, you have what's called a matrix. And a determinant says there's a number associated with this matrix. So for a 2 by 2, the way you determine the number is you do the following. You take the product A times D, and then you take the other product, B times C. So you're forming an X, but you subtract. So it's A times D minus B times C. Okay, well what if we have not a 2 by 2, but a 3 by 3? Well, there's two ways to do this. Now, one of them is something which works really well, but just for dimension 3. So in other words, don't do this in higher dimensions. But it's the following. It says, suppose you have this array of numbers, A, B, C, D, E, F, G, H, I. So start by copying it down. A, B, C, D, E, F, G, H, I, and then copy the first two columns again. A, D, G, and B, E, H. So there's A, D, G, B, E, H. And what you're going to do is you're going to multiply on the diagonals. So we're going to get A, E, I. That's the first diagonal. Then we're going to go across. B, F, G. Okay. B, F, G, and C, D, H. C, D, H. But now we're going to go the other direction. So when we went downhill, we add. When we go uphill, we subtract. So subtract G, E, C. And then we go to the next one, subtract H, F, A. And we go to the next one, subtract I, D, B. And here's the fun fact. That number that you get, that's the determinant. Now, what is that? We'll get to that. We'll get to that. Just wait a minute. By the end of the lecture, we'll say one thing that the determinant can be interpreted as. But there's a second way to do the determinant, and this is sort of a nice method which works for any size matrix. It's called cofactor expansion. And the idea is the following. I'll pick a row or column. It's almost always going to be the first row. So here we go. A, B, C. And now what we're going to do is we're just going to work our way across. So we start with the first entry, A. So that goes there, A. Now cross that out. So in other words, when I say cross out that column, cross out that row, you'll see there's a little 2 by 2 left. E, F, H, I. Now go to the second entry, B, B. Cross that out. D, G, F, I. D, G, F, I. Go to the third entry, C. Cross it out. D, E, G, H. D, E, G, H. But there's one other thing you got to be careful of. You alternate plus, minus, plus. Plus, minus, plus. And now, what happens? Well, turns out that if you do the computation here, what do you get? Well, this would be A, and I'd have EI minus HF. And here I'd have minus B, DI minus FG, and C, DH minus EG. And if you actually go through and check, you'll see that everything matches. So in other words, here if you multiply it out, you get A, E, and I. There you go, A, E, I. And then here you have A, H, and F subtracted. A, H, F subtracted. B, D, I. Well, that's negative. Oh, there it is, B, D, I. Cool. Minus makes plus, a B, and F, and a G. B, and F, and G. Good. And so forth and so on. All right, which one should you know? And the answer is, you should know one of them. Doesn't matter which one you learn. You should learn one of these two. Okay, so anyways, the determinant is that. Now, why did we go this direction? Well, it turns out, amazing fact, if I have two vectors, A, B, C, and D, F, and I take their cross product, that if you take the 3 by 3 matrix, first entries are first row, I, J, K. Second row, first vector, A, B, C. Third row, second vector, D, E, F. And you take that determinant, that is equal to the cross product. Well, let's verify. So how do you verify? Well, we're going to just do the work. I, J, K, A, B, C, D, E, F. So we're taking this cross product, and what do we get? Well, I'm going to do this way. So in other words, I'm going to represent this by copying the work down again, copying it all down, and then repeating the first two. So A, B, C, A, B, D, E, F, D, E. And now I start going down. So I have B, F, and I. So B, F, I. Then J, C, D. So I'm going to put C, D, J, and K, A, and E. So A, E, and K. I'm putting the vector as the last thing. That's the convention. Now, that's the downhill. You add. Uphill, we subtract. D, B, and K. And so I'm going to subtract D, B, and K. I'm going to put that right underneath the K term. All right. Next one, E, C, I. So, subtract E, C, I. And then last term, F, A, J. So, subtract F, A, J. Now, if we put this together, what do we have? Well, in the I component, we'd have B, F, and minus EC, which I'll put that in alphabetical order, minus CE, comma. Next, CD, minus AF. Last one, AE, and then minus, oops, almost about to go off the page, AE, subtract BD. Now, how do we know if it's right? Well, we're going to go back and check the formula. So we have the formula. BF minus CE, CD minus AF, AE minus BD. It works. It works. And now, what's the advantage? Well, you either remember an expression like this, which if you get one little piece wrong, you're in trouble. Or you remember a process, such as this. And if you remember the process, it's less likely that you'll get in trouble. Not zero, but less. All right. So, let's do an example. So we're going to take the cross product of two vectors. And so, here we go. I'll come up with vectors. Let's do minus 2, 1, 4, and 3, 1, minus 5. Why not? Okay, those are two vectors. And let's see what we can say. So we're going to follow the rule here. So I'm going to have I, J, K, minus 2, 1, 4, 3, 1, negative 5. Taking that determinant. Now, I can write it down again. So in other words, I can do I, J, K, negative 2, 1, 4, 3, 1, negative 5. And then first two columns again, I, negative 2, 3, J, 1, 1. And I can follow this, or one thing to notice is I can just wrap around. So for instance, I'll have I, 1, negative 5. Negative 5I. J4, 3, because you'd have J4, 3, so it's J4 wrap around 3. So that's 12J. K minus 2, 1, because again, K minus 2, 1, K minus 2, 1. So that's minus 2K. I'm going downhill, so I always add the result. Now, when I go the other direction, I'm going to subtract the result. So 3, 1k. That's 3k, subtract. So minus 3k. 1, 4i. So again, that would match 1, 4i. 1, 4 wraparound I. 4i, but because I'm going up, subtract. So minus 4i. And then minus 5 minus 2j, which would be this last part. So that would be 10j, went uphill, subtract. So minus 10j. Put this together, well, I get minus 5 minus 4 is negative 9. 12 minus 10 is 2. Minus 2 minus 3, negative 5. All right, that's the cross product, we hope. Well, we want to do more than hope. We really want that to be the answer. Okay, well, that's the next point. So I want to verify that that's in fact the right cross product. So how do I do that? Well, I want to do one of two things. One is I could redo the work, and there's sort of two downsides to redoing the work. One, if you made a mistake, you're probably going to make the same mistake again. And so you don't want to do the work again, if possible. But the other one is it tends to be a lot of work. So what you want to do is find ways to say, is there an easy way to check the answer? Well, here the easy way is to say, hey, the cross product that came out, it has to be perpendicular to what I started with. So it has to be the case that if I take u dot u cross v, I get 0. And at the same time, if I take v dot u cross v, it's got to be 0. Is it 100% guaranteed that if you do that, you're right? No. But for all intents and purposes, especially when we talk about caring about direction, and we're going to do that a lot in the next few lectures, it's good enough. It's good enough. So let's check to see what happens when we look at these dot products. So I'm going to look at negative 2, 1, 4, which is our first vector, and I'm going to dot negative 9, 2, negative 5. Well, let's see what happens. Negative 2 times negative 9 is positive 18, plus 1 times 2, which is positive 2, and 4 times negative 5 is minus 20. Well, put those together, you got 0. All right, well now we'll do the other one, 3, 1, negative 5. So 3, 1, negative 5. And we dot it here with negative 9, 2, negative 5. What do you get? Well, 3 times negative 9, negative 27. 1 times 2 is positive 2. Negative 5 times negative 5 is a positive 25. Well, it's not hard to see. 25 plus 2 is 27. Subtract 27 gives us 0. All right. So this is confirmation. We said, look, we want to build the cross product in such a way so that it's going to have a new vector perpendicular to the ones which came before. And it worked out. It worked out kind of nicely, actually. All right. So that's how we can go about actually computing the cross product. Well, most of the time when we use the cross product, we're going to be focusing our energy on the direction. In other words, finding something which has the right direction, perpendicular to two initial vectors. However, there's another use of the cross product, and that is to find the magnitude. So we have to understand, what does the magnitude represent? So if we start with two vectors, so here I have two vectors, u and v. And there's some angle between them, and so I've put u and v together. Now, you'll see here that it's been drawn in such a way that really this other side is also v, and this side is also u. So in other words, this forms a parallelogram. And what can we say? Well, it turns out that the area of a parallelogram is base times height. Now, if I'm thinking about this picture here, I can think of the base as the length of u. So in other words, I can say it's the magnitude of u. And the height, how do you find that? Well, you drop straight down, forming a right angle, and we'll call that the height. Well, if we look, I have the height is the opposite side, and the adjacent side is the magnitude of v. So the opposite and hypotenuse, I said adjacent, but I meant to say opposite and hypotenuse, that's related by sine. So sine of theta is h over magnitude of v, or, as it says here, the height is the magnitude of v sine theta. So we multiply these together, we get that the area is the magnitude of u times the magnitude of v sine theta. Well, that's the magnitude of u cross v. So in other words, the magnitude of the cross product is an area. That's one way to think about it. Very useful way, which we'll use in the second part of our course. But you might say, look, I don't like parallelograms. I like triangles. Hey, great news. If I want to make a triangle, again, I put my two vectors next to each other. I have my third side, but you could imagine that you extend. And then what do you see? Well, you see it's really part of a parallelogram. In fact, it's 1/2 of a parallelogram. And so we have that the area of a triangle, where the triangle is formed by vectors u and v, is 1/2 the area of a parallelogram formed by u and v. So it's 1/2 the magnitude of the cross product. So let's do an example. So suppose I want to find the area of a triangle with vertices in three-dimensional space. So since it doesn't really matter, I'll go ahead and put 1 at the origin. I'm feeling happy, so I'm going to put 1 at the origin. It doesn't matter. And what do I have? Well, 1, 2, 4, and 3 minus 1, 2. Okay, so what do I do? Well, what's the intuition? I'll draw a picture. So I have 3 points, and I want to find the triangle between these 3 points. And so what I can say is, aha, I really just have to find 2 vectors and take their cross product. Now, which 2? There's a lot of choices, because I have 3 points, so I could have a vector going that way, a vector going that way. So there's 6 vectors. It doesn't really matter. Just pick 2. So I can pick 2 coming out of the same corner. Now, by the way, you might notice that this picture is obviously wrong, because none of these points is at the origin. But we're not here to get the right picture. We're here to get the right intuition. So if we make this corner 0, 0, 0, we can say, well, the 2 sides are 1, 2, 4, and 3, negative 1, 2. So the area is going to be 1/2, 3, negative 1, 2, cross 1, 2, 4. So that's 1/2 of the magnitude of the cross product, I, j, k, 3, negative 1, 2, 1, 2, 4. So let's see, that's, well, 1/2. Let's start working on this cross product. I have I minus 1, 4. So minus 4i. J, 2, 1. 2j. K, 3, 2. 6k. And now, that's going the downhill, going uphill. 1 minus 1k. Well, that's minus k because I went up, I subtract. So I subtract minus k is really plus k. 2, 2i, so that's 4i, but I went up, so I subtract 4i. And then 4, 3j, but again, because I went up, I subtract 12j. So this becomes 1/2, and now we have the magnitude, negative 8, negative 10, and 7. All right, so we're almost there. How do we finish up? Well, that's 1/2 square root of negative 8 squared, 64. 10 squared, negative 10 squared, 100. And 7 squared, that's 49. And if we wanted to, we could say, well, 64 plus 100 plus 49, is 213. So we could say square root of 213 over 2. Good. Nice final answer. All right. Now, suppose we ask the following. Find the area of the triangle with vertices, but now we're not in 3 dimensions. We're in 2 dimensions. So you might say something like, well, 1 and 2, negative 3, 1, 4, 0. Okay, so that's a triangle. But we have a problem. These are not in 3 dimensions. These are 2-dimensionals. So I have a set of points here in the xy plane. So I cannot form 3-dimensional vectors because they're in the xy plane. That's 2 dimensions. Or can I? Well, what can we think about this? There's really another way to think about this and say, look, secretly, these aren't 1, 2, negative 3, 1, and 4, 0. Secretly, it's 1, 2, 0, negative 3, 1, 0, and 4, 0, 0. So in other words, what we're saying is put this xy plane, which is currently like this, it's really something that's sitting in 3-dimensional space. So that this triangle here is also a triangle here. And so, once we put it into 3D, now we can apply the old formulas. So, this is a nice trick, which is to say 2D is inside of 3D. And the reason we do this is because for 3D, we have tools. And once we have tools, we should make good use of our tools. Tools are good to have. All right, one last idea, and then we'll be done with products and ready to move on. So we're going to try to find the volume of a parallelepiped. Now, what is a parallelepiped? Well, probably it's a word that would give you a lot of points if you were able to play it in Scrabble. But what it means is essentially it's like a 3D box. So think of it like a parallelogram. So a parallelogram, we had parallel sides. In a parallelepiped, we have parallel faces. So this face, for instance, over here, is parallel to that face over there. And if you think about it, well, how do you form such a thing? Well, you have really 3 vectors. So u, v, w. And these 3 vectors combine together to form this box. So you piece them together. Now, how do we go about finding the volume of a parallelepiped? Well, it turns out it's actually not too bad. The way you find a volume is you take the base, which has been shaded here, so this is our base, and you multiply it by our height. So that's our height. Now, if you think about it, what's the base? The base, it's a parallelogram. So the area of a base we can find by using a cross product. So if this is u, and here you'll see this is v, in the back, they're right next to each other. So the base is found, the area of the base, by taking the magnitude of u cross v. Ah, cool. Well, we're halfway there. What's left? The height. Well, okay, so we need to think a little bit about the height. So to help us figure that out, we say, well, what can we say? If we think about it, this direction here is perpendicular to my base. So, in particular, the vector u cross v is this direction. So that's the right direction. So what I can say is, well, I want the height. So the height, that's what I'm after. I do know this length, because it's the length of w. And I can find this angle. It's the angle between w and u cross v. So I have all this wonderful information, and if I look a little bit closer, I say, aha, really, all this comes together to form a right triangle. So I have an angle, an hypotenuse, and I'm after the adjacent side. So the height is the following. It's the magnitude of w, which is hypotenuse, cosine theta. So it's how do you find the adjacent side if you know the hypotenuse? It's you use the cosine. So the height is the magnitude of w times cosine theta. Now you'll notice I have an absolute value sign, and the reason that has to be there is because cosine could be negative. So the conclusion is the following. We have the base, we have the height, so putting that together, we get that the volume is the following. The magnitude of u cross v times the magnitude of w times cosine theta, where theta is the angle between u cross v and w. If you stare at this, you say, wait, it's a magnitude of two vectors, cosine the angle between them, that's a dot product. So that's w dot u cross v. And then you take the absolute value just to make sure it's positive. So that's how you find volume. So in fact, it's not a very hard thing to find the volume once you have the right formula. Well, can we say anything more? It turns out the following is true. That if you go back to the cofactor expansion, so that was on one of our sheets when we talked about the determinants, and let's see if we still have that. Yeah, it's right here. So if you think about the cofactor expansion, these entries here, those are the I component, the j component, and the k component of the cross product. And so what's happening is that you're taking the dot product becomes the I component of the cross product dotted with the I component of the original, and so forth and so on. And so it turns out by cofactor expansion that if I want to take a dot product of a cross product, it's the same as taking a 3 by 3 matrix and putting in each row one of the vectors. So what we can say, in the conclusion, the punchline, is that determinants are volumes. So that's what a determinant is. It's a volume of a shape. All right, so last example, and then we're done for the day. So let's find the volume of the parallelepiped whose sides are given by some vectors. So we'll put some vectors in here, and so these are the u, the v, and the w. So I could have like 2, 0, 1, 3, 1, 0, negative 2. Negative numbers are allowed, no problem. 4 and 5. So the volume is done by what? We're going to take the determinant 2, 0, 1, 3, 1, 0, negative 2, 4, 5. And by the way, because we're looking at volume, it doesn't really matter which order we take it. Because it's the same vectors, it's going to be the same parallelepiped. And so once we take the absolute value, it's always going to be the same. Now, the reason here I'm being careful is if you do switch the order, you might end up with a negative. But again, because you take absolute value, that all works out. So what do we have? Well, so this is the absolute value. Let's just take our determinant. 2, 1, 5, which is 10. 0, 0, negative 2. 0, 1, 3, 4. 12. Then we're going to subtract. Minus 2, 1, 1. So it's negative 2, but I'm subtracting. So it becomes plus 2. 4, 0 times 2. Well, that's 0. But remember, we're going uphill, so we subtract. So subtract 0. 5, 3, 0. Multiply them together, you get 0. Again, subtract. And we have 10 plus 12 plus 2, which is absolute value of 24, which means that the volume of this shape is 24. Done. Done. All right. Next time, a new topic.